Hello, everyone, and welcome to the new part of the unit where we're going to learn about logarithms. First, we're going to learn about what is a logarithm. We're going to learn about how to graph logarithms. And also today, we're going to learn about the basics. How do we use properties of logarithms to solve? So, the problem I always start out with when I teach logarithms is x squared equals 16. Most students tell me, okay, x can be 4, because 4 squared is 16, and x can be negative 4. We talk about we can use the square root, and we know how to do that. But what happens if we have 3 to the x equals 16? That is why we need logarithms. I can't take the x root. I don't know what the root is. Can't take the cube root or the fourth root. I'm just not sure what to do. So in math, we created something called logarithms that help us evaluate a problem like that. So by the end of this unit, you'll know how to solve 3 to the x equals 16. Start with a warm-up like we normally do, practice some exponential functions, which are going to be key to helping us with logarithms today. Pause the video, see you can do these problems. We'll move on from there. Okay, apparently that bell means it's time to try the problem out. So let's take a look at the answers. So a population of 30,784 is decreasing by 1.2% each year. What will the population be after 8 years? So we have a starting value and we have a multiplier because we start with 100% and subtract 1.2%. So 98.8%. We could put 8 in for time and then we get about 27,950 people. The second question asks you to make a sketch of the exponential function 3 times 2 to the x. Start at 3, multiplier is 2, so 3, then 6, and the next one's 12. Here's a nice table. Okay, we're going to need this graph today to help us find inverses. We know this is growth, so continue practicing graphing. And if we know what exponentials look like, we know what logarithms look like. We just got to learn a little bit more about logarithms. So what a logarithm is the inverse to an exponential function. It's the undo function. Okay, whatever an exponential function does, logarithm does it but in reverse. So we're going to have a base value, an exponent. We're going to learn about where that button is on the calculator, what it actually does, and something also called a natural logarithm. So what a logarithm is, it's the inverse to an exponential function. It helps us solve or rewrite an exponential using something called a logarithm. Now, a famous mathematician, Mr. Napier, founded logarithms. Fascinating history, but I'm not going to go into that because some of you couldn't care less about math history. So here's our conversion formula. Write down these two formulas. So to go from b to the y equals x, we could rewrite it as log base b of x equals y. And this base that's a smaller number. Okay, we'll see an example momentarily. But we're going to do a lot of writing from exponentials to logarithms and going the other way as well. Depending on what is needed, we can convert between logarithms and exponentials. Generally, if I give you one form, you're going to want to find the other form. And another interesting fact, and really important fact, is if there's no number here, if there's no b value, then the b value is automatically 10. We work in what's called base 10. So your calculator may have a way to change the base, or it may not. You may just be stuck with base 10, and we can definitely work with that, and we'll see different ways we can convert everything to base 10. So sometimes we're allowed to change the base, have a different base in here. Sometimes we're stuck with it being 10. And depending on what's needed, we may have to convert an exponential to a log or a log to an exponential. But these two formulas, crucial. They mean the same thing, but they look different. Now, we haven't talked about natural log much in this class. I would like to go over it briefly to explain what it is. So natural log is the inverse to the exponential constant e. E is used a lot in continuously compounding interest. If you remember p times e to the RT, that's the same e. So if we have e to the b equals a, we can use natural log, and there's really an imaginary e here. Now for most of this course, we won't need the natural log, but as you get further into math, natural logs become important as well. So the same conversion where the base is e, the base down here is e. The exponent is up here, the exponent goes by itself. And then really relates the base to the exponent, and we're going to see an example. So here we don't have to solve, all of these equations are true. 10 to the 4th equals 10,000, log base 6 of 36 equals 2 to the 7th equals 128. I put some variables in here. I just want us to practice converting. How does the exponentials look as logarithms? And how do the logarithms look as exponentials? So I'm going to do the first two examples, do them with you, and then you're going to pause the video and try the next three. So I see the first one's an exponential, so I want to write it as a log problem. Okay, my base is 10, and my exponent's going to go on the other side. So I have log base 10 of 10,000 equals 4. So that's how that problem would look as a log problem. These two mean the same exact thing. Now the second one is a log, and we're going to convert it to an exponential. So the base is 6, and the exponent's by itself, so 6 squared equals 36. And we know that's true. We know 6 squared is 36. Now with just numbers, it doesn't matter whether I have a log problem or an exponential problem, but eventually there's going to be variables in there, and sometimes it'll ask us to solve for x or solve for y, and we want to get a variable by itself. So go ahead, pause the video, see if you can convert these two, so the third one, the fourth one, to log problems, and convert the last one to an exponential problem. When you're ready, unpause the video, show yourself that you can do it and that you got the right answer. Okay, so I'm ready to see right answers. There's correct answers. We talked about the first two. The third one, the base is 2, the exponent's 7. The fourth one, the base is 10, the exponent is y. This one also is interesting because we can write it as log of x, because if the base is 10, we don't need to write the 10. So you'll see a lot of times if there's a 10 as the base, we don't write it. You can write it. It's kind of the same as writing x or 1x. Same idea. And then the last one is different. The base is 3 and the exponent's on the other side. So 3 to the y equals x. So we go from logs to exponentials. If you can smoothly convert between logarithms and exponentials, you're going to be pros at graphing, solving, but it's really key that we can convert from one to the other. Now to graph logarithms, we're going to do exactly what I just told you we do. Convert to exponentials. We learned how to graph exponentials. We're going to be able to graph logs. Except in this case, we're going to pick the y's instead of the x's, and you're going to see why momentarily. And then once you get a few values in your table, plot them. graph them. We're going to see what it looks like. So convert to exponential. We're going to pick some y values, find the x's, and then we're going to plot the points. So let's look at an example together. Okay, we're going to graph y equals log base 2 of x. So step 1, we said, convert it to an exponential. So 2 to the y equals x. Now the next step would be, well, I normally pick an x value and then put an x in and find y. Much easier if I put y in and find x. So if I put -1 in here, okay, I can get a value. If I put 0 in here, 2 to the 0 equals 1. So I have 0 for y, 1 for x. If I put in 1 for y, I get 2 for x. 2 to the first is 2. I can make a bigger table, but those are enough points to help me graph. Now make sure we're still graphing it like we normally do as 1, 0, 2, 1, 1 half, -1. We can graph the points. Okay, and do it on graph paper. No more making your own free-handed graphs that look terrible. You're going to have to see where the asymptote is on this. You're going to have to see that the points look good and the curve is smooth. And it looks like that. 1, 0, 2, 1. We had 1 half -1. So we had like this point here. And now we have a vertical asymptote. So previously we had a horizontal asymptote. Now we got a vertical one. So this is the inverse, the opposite of an exponential function. Exponential function would curve up. This one curves down and becomes flatter. We have these 3 points. We have a vertical asymptote. Okay, after you make your curve, you're going to start seeing which x value the graph doesn't cross. And that's how we graph logarithms. Convert to exponential, make a table of values by putting in some y's, take those points, throw them on a graph, and your logs should always look like this. Okay, we're not dealing with logarithms that are any other shape. They curve up. Okay, they look like that. You're going to practice now. Go ahead. The bottom example is slightly more straightforward than the top one. Top one's going to give you a little challenge though. So try both of them, pause the video, take you 5, 6, 7 minutes, get the correct answers. Okay, so let's see what you did. Okay, I converted, and this top one, ooh, okay, we have x plus 1. We can get x by itself, subtract 1. We could still put y values in. Remember, negative exponents mean fractions. They don't mean negative numbers. 0 exponent is 1, so 3 to the 0 is 1, minus 1 is 0. Put 1 in here, get 3 to the first, minus 1 is 2. Put 2 in here, put -1. Get a few values. Okay, here it's a little more straightforward. Okay, put in y values. Once again, I say I like -1 to +1. In this case, I did -2 to +2. I did a few more. And if you plot the graphs, they look like this. This one, the +1 shifts it over left 1. So instead of our vertical asymptote being the y-axis, our vertical asymptote is left 1 unit. Still got some nice points. Okay, I plotted 2 points. I looked at the curve. I made the asymptote. That's a clear enough graph. I can do that. Now, if you're ever asked to plot the points or graph it, do this process. Exponentials are a lot easier to look at to make tables for, and then we can graph. Now, the last thing we're going to look at is the most prominent reason why we use logarithms, and it's solve. So we're going to solve for x. Now, my warning, every time we learn a new math, does not mean that's the only way we can solve. Some of these can be solved a lot quicker without logarithms. I would never use a logarithm with certain ones of these. In fact, some of these logarithms make no sense. So, if you'd like, you pause the video, try them out. After you try them out, after you look at the solutions, I will go through them one by one at the end. if you have any specifics you'd like to look at for a little bit longer. So go ahead and pause the video, try out which ones you'd like. I'll continue in about 5 seconds. Okay, so keep the video paused if you want to work on it some more. If not, here are the answers. And now we will look at how I did some of them. So this first one, 64 is 8 squared, but this is a fraction, so I know the exponent's got to be negative. Okay, because 8 squared is 64, which means 8 to the negative second is 1 over 8 squared, or 1 over 64. X is negative. Don't use logarithms all of the time. We'll learn a different way next lesson to solve this if we wanted to use logarithms, but sometimes numbers are familiar, we can figure out the x value. Second one, no logarithms. Once again, I can undo a cube root. Take cube root both sides and I get x equals 4. What do I have to undo? That's what I gotta think about. Don't just use logarithms anytime you see an exponent. Might end up poorly. Next one. This one's just evaluate. 3 to the negative fourth is 1 over 3 to the fourth, and 3 to the fourth is 81. And that's what x is. Once again, did not use logarithms. There's going to be very specific cases when we have to use them. This is, once again, not one of them. This one, now I get a logarithm problem. I don't want a logarithm problem. So I'm going to convert this to an exponential. 5 to the x equals 125. How many 5s do I need to multiply to make 125? 3. 5 times 5 times 5 is 125. Hopefully we know that. If not, it's okay. But I converted to an exponential first, and I know how to get the value of x. This one, once again, going to convert to an exponential. Base is 3, exponent's 2. Now this is a very straightforward problem. I do it. If I see a log, I generally want to convert to an exponential. If I see an exponential problem, I think, can I solve it or do I need to use a log? So far I haven't, but maybe there's a case where we will. Definitely next lesson. This one, once again, log. Convert to an exponential. And this is not even an exponential, it's just one with an exponent. X to the negative 2 is 1 over x squared. And I need to know a number squared equals 81. I think I know 9 equals 80. 9 squared equals 81. So practice converting between logs and exponentials. See which one helps you graph easier. Which one could you put values in? Especially with solving. Generally, whatever I see, I might do the opposite. Start with log, go to exponential. Start with exponentials, sometimes I'm going to go to logs. And next lesson, we're going to see where the real use is for solving, especially when we have a variable in the exponent.